participants of the conference, esteemed colleagues, and dear friends from the whole world. It's my great pleasure and a big honor speaking here. Thank you for your participation in our conference during this terrible time for Ukraine. Your presence here is not only an academic gesture, but also profound act of solidarity and support, for which we are deeply grateful. I wish all of us productive discussion and inspiring discoveries. Today we are talking about derivations, automorphisms of infinite dimensional algebras. And let us start from the very beginning. Some definitions, examples. We'll call a linear mapping a derivation if it satisfies the product rule on the slide. And some examples. The first, if we consider an algebra of polynomials of finite set of variables, then the finite sum on the slide is a derivation, and every derivation is of this type. Some another example. We consider a joint derivation in the case of associative algebra, inner derivation as a commutator in the Lie algebra, and the set of all derivations form a Lie algebra of all derivations. And what about automorphism? Also, let me recall the invertible linear mapping is an automorphism if it satisfies corresponding product rule on the slide too. And also, this set of all automorphisms forms a group, automorphism group. Some remark about the connection between derivations and automorphisms in some meanings topological on another one. When we consider exponential series, for example, some on the slide, but such series that make sense, as I told before, in topological in another sense, then such infinite exponential series is automorphisms. Therefore, in that meanings, derivations are infinitesimal automorphisms. In some meaning, I will use it. I will use it later. Let me recall some results from my talk from the previous algebra conference, because this talk contains that work. First of all, let me denote the algebra of finite matrices by symbol M sub n. And let us consider ascending chains of such matrix algebras with embedding. And let us denote the union of such increasing chains of matrix subalgebras by symbol M sub infinity. And this algebra consists of the infinite countable matrices which have infinitely many non-zero entries. Next algebra, we will consider the algebra of matrices, countable matrices that have infinitely many non-zero entries in each column. And this matrix is sometimes I will call big one, previous one, we will call it small one. And we consider an intermediate algebras which consist of the countable matrices that have infinitely many non-zero entries in each row and each column. And small one is an ideal in the intermediate, and intermediate is subalgebras of the big one. We also consider for each that associative matrix algebras. We also consider corresponding Lie algebra, and let us denote the corresponding Lie algebra by symbol JL sub infinity, JL sub finitary, and JL subset of positive integers, because we consider a countable case. And also sometimes I will use the name as small, intermediate, and big one Lie algebra. And we also consider a special linear cell sum infinity, which is coincide with commutator of the small Lie algebra JL sub infinity. The small associative algebra M sub infinity equipped with involutions or transpose or symplectic involution, therefore, that algebras gives rise to the algebras of skew-symmetric elements, orthogonal or symplectic algebras, and we would use the symbol by O sub infinity and P sub infinity. And now we will describe derivations and automorphisms of the following algebras: special linears SL sub infinity, orthogonal, symplectic, GL sub finatory, and GL sub set of positive integers. We will not assume that characteristic have some for example, did not equal to 2 or some example. But right now, in the following two theorems, we assume that characteristic of the field is not equal to 2. And the first theorem is about derivations of the special linear symplectic and orthogonal algebras, and arbitrary derivation is a joint derivation by the element from the intermediate algebra GL sub finatory, and this element, in the case when we consider orthogonal or symplectic, is a skew-symmetric relatively to corresponding involution, and all derivations of the intermediate and big Lie algebras are inner. Next theorem about automorphisms. Before, let us denote by symbol GL sub finatory the group of invertible infinite matrices. Let me recall with finitely many non-zero entries in each row and each column, but such that the invertible matrices and its inverse belongs to the M sub finatory, because may happen that invertible matrices belongs to M sub finatory, but inverse doesn't. And next theorem about automorphism. Let me recall that characteristic of the field right now is not equal to 2. So the first, every automorphism of the special linear algebra L sub infinity is a conjugation or anti-conjugation by the element from this group GL sub finatory, and automorphism of orthogonal or symplectically algebra is conjugation by the element also from the group GL sub finatory. Moreover, this element is orthogonal or symplectic with respect to the definition, defining evolution. And the last part, that all automorphism of the intermediate and the big Lie algebra is conjugation by the corresponding group GL sub finatory and the analogical GL subset of positive integer, respectively. Some remark. Theorem 1, part 1, and theorem 2, part 1 and 2, in the case then the field of characteristic is equal to 0, is due to the result of the Carl-Formal net this paper in 2005, and automorphism from paper of Nina Stuman in 2001. Theorem 1 and 2 for fields of characteristic not equal to 2, we prove it in a paper in the Journal of Linear Algebra and Applications. We did such result for generalized in some meaning to Mecke groups and Mecke algebras, but also in the case then characteristic not equal to 2. Of course, what we do in case of characteristic 2, when I did some talk in algebraic seminar in Institute of Mathematics, Professor Yuri Drost asked what about characteristic 2, and digression, is characteristic 2 important? Of course, when we consider some problem, algebraic problem that coming from analysis of physics, it will be probably not. But When we consider a problem that coming from the group theory, it's really yes, because all non-cyclic finite simple groups have even order, and moreover, the main Sylow subgroup of the finite simple group is 2 Sylow subgroup. So what about characteristic 2? Let me recall some previous results. Karl Kurlenop and Nina Stumann relied their result on the representation theory on the finite dimensional simple Lie algebras over a field of characteristic 0, and in positive characteristic that theory becomes more complicated because it doesn't work. In a paper in journal Linear Algebra and Application, our approach divide into 2 steps. In the first steps, we represent every automorphism of the Lie algebra as a combination of a homomorphism and anti-homomorphism, but using the underlying associative algebra. I stressed this place because in another case it also doesn't work. And here we rely to the series of papers by Vidar, Brichard, Chebotar, and Martin Delfort. In that series, Vidar, Brichard, Chebotar, and Martin Delfort proving Herstein conjectures. And next step, then we describe all automorphisms and anti-automorphisms of underlying associative algebra itself. In the second case, characteristic is irrelevant, but Vidar, Brichard, Chebotar, and Martindale assume that when we prove in Herstein conjectures, that characteristic of the field doesn't equal to 2. This was the main difficulty. To address it, let us discuss Lie isomorphisms. So let me also recall some definition. We consider a linear mapping, and we will call linear mapping a Lie isomorphism if it's isomorphism of the Lie algebras. It means that this linear mapping is bijective, such that it satisfies the corresponding satisfies condition on the slide. And then such linear mapping is a homomorphism of associative algebra, then this condition holds automatically. In the case, then this linear mapping is anti-homomorphism, this condition holds as well. And very important for us definition, standard Lie homomorphism. I mean that let us consider 2 homomorphism and homomorphism and anti-homomorphism, such that the product of images of these homomorphism and anti-homomorphism of the elements from our associative algebra is trivial, and then we consider a difference of this homomorphism and anti-homomorphism, and this difference is a Lie homomorphism that we call a standard one. There are a lot of literature on Lie-Jordan homomorphism and sufficient condition to them to be a standard. In particular, a result again Vidar, Brichard, Chebotar, and Martin Delfort. They treated the case, then the algebra in B prime, but characteristic is again not equal to 2. And then one more definition. Let us consider some idempotent. Then the idempotent we will call a full if the ideal that generated by this idempotent coincide with whole algebra. And the next theorem from our joint paper with Irina Kashuba and Yukim Zilmanov, we prove that in the case when we consider associative ring with unit, We consider the ring that contains three pairwise orthogonal full idempotents with some of them which is equal to unit. Then the arbitrary isomorphism from the commutator of this associative ring into commutator of some another ring leads to a standard one. This theorem doesn't contain any restriction of the characteristic, but it's still not directly applicable to the algebra M sub infinity. Let me recall the algebra that consists of the countable matrices that have infinitely many non-zeros entries in each row, in each column. Because our algebra, our associative ring or algebra does not have a unit one. Some more definitions. Annihilator, let me recall, annihilator is the set that consists of the such element from the algebra such that the product of this element from the element from the algebra of algebra from right hand side is trivial, and we will call Lie homomorphism annihilator by standard if we consider a Lie isomorphism such that its corresponding induced Lie homomorphism from our algebra into quotation by the another algebra to the annihilator is standard. So such Lie isomorphism we will call annihilator by standard. And the next theorem, without any unit in the associative ring, also from our joint paper with Irina Kashuba and Yukim Zigmanov, in the case that we consider associative ring that contains again three pairwise orthogonal idempotents, and let us consider some more idempotents which equal to some formal unit minus the sum of these pairwise orthogonal idempotents that satisfy the condition of the full idempotence. Then any Lie isomorphism from the commutator of our associative ring into commutator to some another associative ring leads to annihilator by standard one. Both theorem from our joint paper in the journal Mediterranean Journal of Mathematics, and we also extend this result to isomorphisms of the algebras of skew-symmetric elements. So therefore, we can say that theorem 1 and 2 and results on Mecke algebras holds without any restriction on the characteristic. Now let us back to the example 1. And now we will discuss connection between theorem 1 and 2 to derivation of polynomial algebras. We don't use the result that we are talking about before because our polynomial algebra from the example 1 doesn't have corresponding underlying associative algebra. So what can we do in this case? We consider, in this case, we consider a field of characteristic 0. And let me recall the polynomial algebra of finite set of variables, the derivation of the finite sum on the slide, and the set of all derivations of the polynomial algebra we denote by symbol Wn. Some previous result in 1973 Tekens, and in 1976 Morimoto proved that every derivation of the Lie algebra Wn is inner. In 1969, Rudakov proved that every automorphism of the Lie algebra Wn is the conjugation by the element from the automorphism group. There are another proofs of this theorem. They are given by Bavola and Krah. So let us back for some analogic in the case of the polynomial algebra. And also let us consider ascending chains of polynomial subalgebras, corresponding ascending chains of the Lie algebras, and the union of these ascending chains. We will call it W infinity, and I will use a name small one. This small one belongs to the big one algebra of all derivation that consists of the infinite sum, the corresponding form on the slide. And we will consider intermediate algebras a little bit later. But before, in 1998, Dokovic and Zhao proved that every derivation of the big Lie algebra is locally inner. Locally inner, it means that for every finite dimensional subspace from our Lie algebra of derivation will exist an element such that the derivation X of the elements from these finite dimensional subsets as commutator. We prove stronger results in our joint paper with Irina Kashuba. Every derivation of the big Lie algebra is inner. And let us back to the question, what about derivation of the algebra W of infinity? Are they all inner? Let me recall, it's locally inner. Consider for that intermediate algebra W subfinitary that consists of the infinite sum such that every variable occurs in only finitely many polynomials. Of course, small Lie algebra is an ideal of the intermediate, and the intermediate is a subalgebra of a big one. Now we need some topology. Thank you for your previous talk. And let us consider, topology. We consider a tails of polynomial algebra on the slide. And in this topology, our polynomial algebra of polynomial is not a topological algebra, but when we consider vector space, it's a topological. So then our intermediate algebra, the W subfinitary, consists of the derivation that are continuous is that topology, and therefore, due to the algebra W of infinity is an ideal of the intermediate algebra, any element from the intermediate algebra define a derivation of the small one as a commutator. Next theorem from our joint paper also with Irina Kashuba, we describe a derivation of algebra W of infinity. All derivations is a commutator, is an adjoint derivation by the element from the intermediate one. Therefore, the Lie algebra of algebra W of infinity is isomorphic to the intermediate algebra W subfinite. Only short remark about the proof. We use, in some meaning, of course, the analogy between special linear algebra cells in sub-infinity, W infinity, JLS subfinitary, W subfinitary, JLS subset of positive integers, and corresponding big one Lie algebra. Still open question from paper of Dokovic and Zhao in 1998. Is the big Lie algebra simple? And what about automorphisms? Conjecture that the group of automorphism of the Lie algebra W of infinity is consists of the conjugation such that the conjugation by the element from the automorphism group of polynomial algebra, such that this conjugation, the such element and its inverse are both continuous. And the last slide. Thank you for your attention.